Infrastructure determines whether ML work stays theoretical or becomes repeatable in production. This chapter focuses on the tools and systems that make ML development, deployment, and maintenance possible at real companies. A team may know the right steps for training, deploying, and monitoring models, but still be blocked by the systems around them. The practical problem is often not the model logic itself, but the lack of tools that make that logic usable day to day. ML systems become easier to build when repeated tasks are handled by reliable infrastructure. That saves specialized effort, lowers the chance of mistakes, and makes it easier to ship and maintain applications. When the setup is poor, every change becomes harder and more expensive. A simple analytics workflow may need very little beyond notebooks and standard Python tools. Once the use case is small and self-contained, extra infrastructure can be unnecessary overhead rather than a benefit. Some applications push far beyond standard tools because their constraints are unusual. A self-driving system has tight latency and safety requirements, while a search engine has massive throughput requirements. So companies in those settings often build infrastructure that matches those demands. The common case is a company with several standard ML applications running on data measured in gigabytes or terabytes per day. That scale is large enough to benefit from solid infrastructure, but not so extreme that every system must be invented from scratch. That middle ground is where standardized infrastructure matters most. The rest of the chapter focuses on the tools that help the majority of ML teams work effectively at that level. The figure places simple use cases, common production systems, and highly specialized systems on the same spectrum. The important idea is that infrastructure grows with complexity and scale rather than following one fixed recipe for every company. That spectrum explains why different teams invest in very different tools. A company should match infrastructure to its actual workload, not to an abstract idea of what a mature ML stack ought to look like. In ML, infrastructure is the base layer that lets data and models be created, tested, and kept running. The exact set of facilities changes from company to company, so the useful way to study it is by layers. The first layer is the raw foundation, where data lives, and where computation happens. Every other ML tool depends on these resources being available and reliable. Storage is the place where collected data is kept, and compute is what trains models or generates features. Without those two pieces, there is no environment in which an ML workflow can actually run. The next layer is about coordinating shared compute so it is used efficiently. Once several jobs compete for the same resources, scheduling and orchestration become necessary. These tools help control when jobs run, in what order, and under which conditions. They turn a collection of separate tasks into a managed workflow that makes better use of limited compute. Above that sits the layer that helps people build ML applications more efficiently. It adds shared services that many projects can reuse instead of rebuilding from scratch. A platform may provide places to register models, manage features, and watch how models behave after deployment. Those services reduce duplicated effort and make production work more consistent across teams. The final layer is the space where practitioners spend their daily time writing code and running experiments. Because that work happens constantly, the environment has to support versioning, testing, and experiment tracking. That discipline matters because ML work changes quickly and needs to stay reproducible. If code and experiments are recorded well, teams can compare results, debug problems, and move work forward without losing history. The foundation comes first because data and compute are the resources every ML project depends on. That layer is also the easiest to reason about, so it makes sense to start there before moving into more abstract tooling. The diagram organizes the stack from the foundation upward. Track how storage and compute support the layers above them, and how the development environment sits closest to the work that data scientists touch every day. That layered view helps separate basic resources from higher-level tooling. It also shows why some parts of infrastructure feel abstract, while others are visible in the daily workflow of the team. The development environment matters most to the people writing code and running experiments every day, so it tends to feel concrete rather than distant. The platform layer comes later because it is newer and more complex, and because its value becomes clearer once the lower layers are understood. Even with similar requirements, companies make different build versus buy choices. Those decisions shape the final stack, and they also determine how much standardization is possible across teams. That question of what to build internally and what to outsource will matter later in the chapter. The larger theme is whether ML infrastructure can become more unified, so different teams can rely on the same abstractions instead of inventing their own. Storage holds the data, and compute is what acts on it. The whole point of this topic is to separate where information lives from the resources that process it. The storage layer is the place where raw data ends up before any model uses it. It might be a local disk, a cloud bucket, or a data warehouse. And the main change over time is that storage has become cheap and widely available. So most companies no longer build it from scratch. Compute is the set of machines and services that actually run your workloads. More compute means you can train, infer, or process data at larger scale. And in practice, that usually means cloud instances from providers like AWS or GCP. A compute layer is usually divided into smaller units, so work can run at the same time. Some units exist only for one job and disappear afterward, while others stay around as instances or virtual machines that you keep using over time. Different systems define a compute unit in different ways. Spark and Ray think in terms of jobs, while Kubernetes uses pods, so the smallest unit depends on the abstraction layer rather than the physical hardware underneath. A job only runs after the needed data is in memory, because operations like addition or convolution happen on in-memory values. If the data does not fit, the computation stops being straightforward, which is why memory size matters so much. Memory is usually measured in gigabytes, and more memory means a compute unit can hold more data at once. Speed of moving data in and out also matters because high bandwidth lets the machine keep feeding the next operation instead of waiting. A common speed metric is flops, which counts floating point operations per second. Vendors use it to describe GPUs, TPUs, and other accelerators, often with very large numbers like teraflops. That number is not the whole story, because different vendors may count operations differently, and real jobs rarely reach the hardware limit. Utilization tells you how much of the machine's theoretical speed the workload actually uses, and low I/O bandwidth can keep that utilization down. A better test is to measure how long the machine takes on tasks that resemble real work, such as training ResNet 50 or running BERT-large predictions. Benchmarks like MLPerf make performance concrete because they connect hardware choice to job completion time. Because flops is hard to interpret, people usually compare instances by core count and memory size instead. In cloud systems, you also have to translate vendor terms like vCPU into physical capacity, since those labels do not always mean a full core. The figure compares real cloud instance choices, so the main thing to track is the trade-off between core count, memory, and accelerator type. Those are the numbers that shape what kind of workload each instance can actually handle. The labels in the figure help tie the abstract idea of compute capacity to real cloud offerings. What matters here is not the brand names alone, but the combination of instance size, memory, and hardware accelerator that determines how much work each machine can carry. Public cloud and private data centers are two different ways to pay for and control compute. The trade-off is usually convenience and flexibility on one side, and tighter control or lower long-term cost on the other. Compute has become a commodity, so many companies avoid building their own capacity from scratch. They rent exactly what they need from providers like AWS or Azure, which is especially useful when workloads rise sharply during experimentation and then settle down in production. That elasticity matters a lot in machine learning, where development often creates short bursts of heavy compute demand. Cloud capacity is flexible, but still has boundaries. Providers set quotas, large instances have practical limits, and cheap capacity like spot instances can be harder to rely on. So the cloud removes a lot of infrastructure burden, but it does not remove the need to plan for scale carefully. That shift shows up in industry spending data. More companies are choosing the cloud early because it is faster to adopt and easier to manage, so the money follows that convenience. The chart below captures that movement clearly. The key comparison in the figure is the growth in cloud infrastructure spending versus the decline in data center spending. The direction matters more than the exact numbers. Companies are steadily moving operating dollars toward rented infrastructure instead of owned facilities. The figure makes the market shift concrete. Cloud infrastructure kept growing fast, while traditional data center spending moved the other way. That contrast sets up the next question, which is when cloud use stops being the cheapest choice. Early on, the cloud often wins because it lowers the barrier to entry. As usage grows, though, infrastructure can become a very large share of revenue, and that makes the cost structure much less comfortable for mature companies. At that point, the cloud bill itself starts to shape business decisions. When cloud costs get too high, some companies shift workloads back in-house. Dropbox is one example, but the pattern is broader. Cloud margins can matter enough to affect company value, not just engineering budgets. That is why infrastructure choice becomes a strategic decision, not just a technical one. The hard part is the exit. Moving workloads back requires capital, engineering time, and careful planning. So many companies end up with a hybrid setup instead of full reversal. They keep the cloud where it works well and build owned infrastructure gradually where it pays off. Another response to cloud dependence is to spread workloads across more than one provider. That can reduce lock-in, but it also adds coordination cost, so the operational trade-off changes again. A multi-cloud setup gives a company more negotiating room and more technical options. Teams can choose services from different providers instead of being tied to one stack, which helps when one provider has a better price or a better machine learning service. The downside is that every cloud has its own tools, so portability takes real design work. In practice, multi-cloud is usually painful rather than elegant. Data movement, orchestration, security, and networking all become more complicated when the infrastructure is split across vendors. That difficulty is why many teams end up with multi-cloud for necessity, not because it was the original plan. Separate teams often choose separate clouds, and acquisitions can leave two different infrastructures sitting side by side. Once that happens, the organization may live with multiple clouds for a long time because migration is expensive and disruptive. Multi-cloud then becomes a fact of the company structure, not a deliberate architecture choice. Investor relationships can influence cloud choice as well. If a strategic backer is Microsoft or Google, some companies gradually move workloads toward Azure or GCP because the business ties make that shift worthwhile. Infrastructure decisions often follow organizational incentives just as much as technical ones. The development environment is the place where code gets written, tested, debugged, and prepared for deployment. A strong setup here matters because it shapes how fast engineers can work and how reliably changes move toward production. ML work does not happen in isolation. Engineers build in one place, run experiments in another, and need a clean path to the production environment where champion and challenger models are compared. Many teams spend a lot of energy on production systems, while the daily coding and testing workflow stays messy and improvised. That gap slows people down because weak tools at the start make every experiment and bug fix more expensive. If only one layer of infrastructure gets attention, this is the one that pays back immediately. Better development tools reduce friction for the people doing the work, and that shows up directly in engineering speed and quality. The path forward is straightforward. Identify the pieces of the development environment, make them consistent across the team, and then use containers to carry those changes into production. That sequence turns day-to-day coding habits into a repeatable workflow. A good development environment gives engineers the tools they need to write, test, version, and reproduce machine learning work without friction. Versioning matters more in ML than in many other software projects because so many parts can change at once. The code, the parameters, the data, and even the train model itself. Tools like Git, DVC, weights and biases, Commit.ml, and MLflow help keep those pieces tied to each run so you can reproduce results later. A test suite catches problems before deployment, which is why CI/CD belongs in the environment around the code. It automates checks after changes are pushed, so bad code does not move forward unnoticed. The IDE is the daily workspace, so it shapes how quickly someone can write, edit, and understand code. That makes it the most practical place to start when thinking about the development environment. An IDE is the editor and workspace where code gets written and reviewed. The main idea to keep in mind is that it is not just a text box. It is the tool that supports the whole coding workflow. Some IDEs are installed on your machine, like VS Code or Vim, while others run in the browser, like AWS Cloud9. The important point is that the editor often does more than plain text editing by supporting multiple languages and development features. Notebooks are useful when you want code mixed with results and visual artifacts in one place. That makes them especially good for exploratory analysis and for inspecting how a model behaved during training. A notebook can keep variables and loaded data in memory, so you do not always need to restart from the beginning. If a run fails halfway through, you can fix the failed cell and rerun just that part, which saves time with large data sets. The key idea in the figure is the save state between cells. Steps 1 through 3 stay available, so the failure at step 4 does not force you to repeat the earlier work. That speed is the main advantage of notebook statefulness, especially when earlier steps are expensive to compute or slow to load. The same state that makes notebooks convenient can also make them tricky to reproduce. Cells can run in different orders, so a notebook may depend on a hidden sequence unless the execution order is carefully documented. The figure captures the problem clearly. Notebook cells do not have to follow a strict script order. That flexibility is useful during exploration, but it also means the same notebook can produce different results if the state is not controlled. That trade-off is why notebooks need discipline. Convenience during experimentation, but careful structure when someone else must rerun the work. Because notebooks are so useful for exploration, some organizations treat them as a central part of their data science workflow. Netflix, for example, described tooling that makes notebooks easier to manage at scale. Papermill is one of the tools that extends notebook workflows. It helps turn a notebook into something you can run with different parameter sets instead of treating it as a one-off document. That makes it useful for experiments where the same notebook needs to run many times with different settings. It can also help gather results from those runs into a single summary. Commuter is another notebook tool in that ecosystem. Its role is less about execution and more about helping people navigate and share notebooks inside an organization. That kind of hub matters when many people are creating notebooks and others need to reuse them. Central discovery and sharing reduce duplicate work and make notebook knowledge easier to spread. Dev pushes the notebook idea further by bringing documentation and tests into the same place as the code. That helps close the gap between exploratory work and a project that can actually be maintained. Standardizing the dev environment cuts down on avoidable failures and makes every developer work from the same baseline. That means the same tools, the same versions, and fewer surprises when code moves from one machine to another. A shared setup matters because small differences between laptops can turn into big debugging sessions. When the environment is consistent, problems are more likely to come from the code itself, not from someone's machine. At first, the team only needed a script, a fresh conda environment, and a package list to get started. The trouble began when packages were named without versions, because then two computers could install different releases and behave differently. Writing the exact version next to each package removes that source of drift. Even matching packages is not always enough. A bug can hide in one Python release and appear in another, so agreeing on the Python version is part of standardizing the environment, not an extra detail. When the team hit hardware-specific trouble, the fix was to move the whole setup onto cloud machines. That keeps the same tools and packages, but it also puts everyone on the same kind of computer, which removes another layer of mismatch. A cloud environment can come with its own editor in the browser, or it can simply host a machine you connect to. Tools like SageMaker Studio and Cloud 9 Live in that space, though many engineers still prefer to install their own editor on the remote machine. A common setup keeps the editor on your laptop and the code on a remote machine. With SSH, the local editor feels familiar, while the actual environment stays standardized in the cloud. Tools and package versions are usually easy to standardize, but IDEs are more personal. VS Code tends to fit cloud workflows well because it connects cleanly to remote instances without forcing everyone into an unfamiliar editing experience. Cost worries often fade once the environment shuts itself down after inactivity and the machine size is chosen sensibly. If a cloud setup prevents repeated setup problems and saves engineering time, that time savings can matter more than the hourly machine cost. Centralized machines make support easier because IT only has to understand one standard setup. They also make remote access simple and let a stolen laptop be cut off from the codebase, although some companies still cannot use the cloud because of policy or data restrictions. For teams running production in the cloud, this is often the strongest argument. When development and production live in the same kind of environment, fewer bugs are caused by differences between where code is written and where it finally runs. Some workloads cannot be copied to a laptop at all, especially when data must stay in the cloud. In that case, a cloud notebook with access to the right storage and permissions is not just convenient. It is the only practical way to work. Cloud dev environments are not the right answer for every company because cost, security, and training all matter. Still, when the setup fits the organization, standardization usually pays off by making work smoother for data scientists and reducing wasted effort over time. Production changes the problem from a single stable machine to many machines that appear and disappear as demand changes. Containers solve the hard part of making each new machine ready to run the same workload. During development, a fixed machine is usually enough because the workload stays small and predictable. You can install things once and keep working in the same environment. Production is different because traffic can jump without warning, so the system has to add instances on demand. Those new instances still need the right tools, packages, and model files before they can handle requests. Cloud providers often take care of launching and stopping instances automatically. The remaining problem is making each new instance match the environment your application expects. A long-lived machine can keep its installed tools, but a fresh instance starts empty. That is why production environments need a repeatable set of instructions that can rebuild the software stack every time. Container technology answers that rebuild problem by packaging the setup steps in one place. A Docker file can install packages, fetch models, set variables, and prepare the runtime so the same code can run on different hardware. The Docker file describes how to build the environment. The image is the built artifact, and the container is the running instance. That distinction matters because one image can produce many separate containers. You do not always start from nothing. A base image can already include major libraries, and then you add only the pieces specific to your application on top of it. Once an image is built, it needs a place to live and be distributed. A registry gives teams a central store for private or public images, which makes deployment and sharing much easier. The example that follows is meant to show the pattern, not a production-ready setup. The useful part is seeing how each instruction adds one layer of the final environment. The first step starts with the base environment, which gives the container its starting point. PyTorch comes first because the application depends on it. Starting from a ready-made PyTorch image saves time and avoids rebuilding those core libraries yourself. The next setup step adds an external dependency that the project needs for model training. Apex is pulled in because it provides extra training-related tools, especially for GPU performance. The clone, install, and package build steps turn source code from another project into something available inside the image. Another step sets the location where the application code will live and run. The working directory tells later commands where to operate by default. That keeps the build organized and makes the image behave the way the project expects. The final setup step brings in a project-specific library code. Transformers gets installed last because it depends on the base system already being prepared. At that point, the image contains both the platform libraries and the application libraries needed to run the workload. The first line selects the PyTorch base image, and the run lines add Apex by cloning its repository and installing it with the CUDA and C++ extensions enabled. The worker line sets the project folder, and the final run line pulls in transformers so the image ends with the libraries needed for the application. One container is not always the best fit for the whole pipeline. If different stages stress different resources, separating them lets each stage run on the kind of machine it actually needs. Containers also help when software requirements clash. If one step needs an older library version and another step needs a newer one, keeping them apart avoids dependency conflicts. Once the number of containers grows, manual management becomes impractical. Docker Compose helps on a single host by coordinating several containers together. Kubernetes goes further by coordinating containers across multiple machines. It handles communication, scaling, and replacement so the system can keep running as demand changes. Kubernetes has become a standard production tool, but it can be awkward for data science workflows. That tension is why many teams look for simpler ways to package and run their workloads before reaching for the full orchestration stack. Resource management starts with a simple trade-off: how much compute, storage, and engineer time to spend to get the best result. That trade-off changes a lot between old data centers and cloud systems, so the way we think about resources has changed too. When resources are limited, giving more to one workload usually means taking something away from another. That forces careful planning, and a lot of engineering effort goes into squeezing maximum use out of every machine. Once resources become elastic, the hard problem changes. Instead of protecting a fixed pool, the question becomes whether extra spend creates enough value through revenue, reliability, or save time to justify it. That is why companies often prefer spending compute over spending people. If automation or extra hardware lets engineers avoid manual work and focus on higher value problems, the less efficient resource use can still be the better business decision. ML workflows have to make these same choices every day: where to place jobs, how much capacity to reserve, and when extra cost is worth it. The examples here focus on cloud systems, but the same ideas carry over to private data centers too. Cron handles fixed-time jobs, schedulers handle workflow order and job conditions, and orchestrators handle the machines underneath. The point is to separate when work runs, how work depends on other work, and where the compute comes from. Two properties shape ML resource management: jobs repeat on a schedule, and jobs depend on one another. Once those are clear, the right tooling becomes much easier to choose. Training, scoring, and data preparation usually happen over and over again. A model might retrain every week, while predictions might refresh every few hours, so the system has to handle recurring work reliably and cheaply. Cron is built for one narrow job. Start something at a known time and report whether it succeeded. It does not understand branching logic between tasks, so it cannot express a workflow where one path happens on success and a different path happens on failure. Many ML pipelines are not just repeated tasks. They are ordered chains of steps. Each step may need the output of the previous one before it can begin, so the relationships matter as much as the timing. The first step starts the pipeline with data access, before any modeling can happen. That data extraction stage gathers the raw inputs for the rest of the pipeline. Nothing downstream can be trusted until the right slice of data has been collected. The next stage depends on that data being available and complete. Feature extraction turns raw records into model-ready variables. That transformation has to wait until the data pull finishes successfully, because features built on partial data would be wrong. After features exist, the pipeline can branch into separate training jobs. At this point, the same feature set can feed more than one training run. Parallel branches like this are common, especially when you want to compare candidate models under the same conditions. Once both models finish, the pipeline can move to evaluation. Evaluation depends on both training jobs being done, because the comparison only makes sense when A and B are measured against the same test data. That step decides which model is better on the metric that matters. The final action depends on the comparison result, not just on completion. That is a conditional dependency. The pipeline chooses a different path based on the evaluation outcome. A simple timer cannot express that kind of logic, but a workflow system can. A graph is a clean way to draw those execution rules. Each node is a task, and each arrow says which task must finish before the next one can run, including branches that depend on success or failure. Track the arrows from data pull to feature extraction, then from features into the two training branches, and finally into comparison and deployment. The direction matters because it shows what must happen first, and the lack of loops matters because the workflow has a finite end. A directed acyclic graph is the standard shape for workflow control. Directed means the arrows encode order, and acyclic means the graph cannot loop back on itself, and keep the job alive forever. That graph structure is not specific to machine learning. It shows up in many computing systems. Workflow tools like DAGs because they make ordering and dependencies explicit, which makes automation much easier to reason about. A scheduler takes the DAG and turns it into actual execution decisions. It can launch tasks from events as well as time. It can decide what happens after success or failure, including retries. Schedulers also have to manage scarce compute. They queue jobs, prioritize them, and match each job with a machine that has enough memory and CPU while waiting for that machine to become free. Slurm makes the resource request explicit. Job name, runtime, memory, and CPU count all get declared up front. That information helps the scheduler decide when and where the job can safely run. The first directive names the job, then the runtime limit, then the memory per CPU, and finally the number of CPU cores. Those fields tell the scheduler what resources to reserve before the job begins. People often ask for more memory than they truly need, so a smart scheduler tries to estimate actual usage. If it can reclaim idle memory or CPU from one job, it can keep the cluster busier with other work. A scheduler has to stay reliable while coordinating many machines and many workflows at once. If it fails, every workflow that depends on it can stall at the same time, so the control plane itself becomes critical infrastructure. Schedulers operate at the workflow level, while orchestrators operate at the machine and cluster level. When demand grows, the orchestrator can provision more instances so the scheduled work has somewhere to run. Kubernetes sits at the infrastructure layer and manages containers across machines or clusters. Many teams use managed services like EKS or GKE because running and maintaining a cluster yourself is a lot of operational work. The boundary is blurry because real systems often combine both roles. Some platforms schedule on top of an orchestrator. Some orchestrators include scheduling features, and tools like Airflow, Argo, Prefect, and Dagster add their own orchestration and scheduling layers for data and ML jobs. Data science workflow tools sit between individual scripts and full production systems. The useful question is what they automate, what they hide, and where they still depend on schedulers and orchestrators underneath. Those tools manage data workflows, but they do it in slightly different ways, so the scheduler versus orchestrator distinction becomes practical rather than abstract. The rest of the discussion places each tool in that landscape and shows why the differences matter for real projects. The basic model is a directed acyclic graph, or DG, where each node is a task and the arrows define order. A workflow can be written in Python or YAML, but the important idea is the same. Each step depends on the results of earlier steps. Most of these systems include scheduling logic for the workflow as a unit, not just for one job at a time. After the workflow exists, another layer handles resource allocation and execution, so scheduling and orchestration work together. The figure separates definition from execution. First, the workflow is declared. Then the system decides when each task runs and what resources it needs at runtime. That separation is the core pattern to keep in mind. Once the graph exists, the platform becomes responsible for turning dependency edges into actual runs on machines or containers. The goal now is not to rank every product, but to compare the features that workflow systems tend to need. Looking at a few widely used tools makes the trade-offs much easier to see. Airflow helped define this space early on, and its strength is the large ecosystem of operators for clouds, databases, and storage systems. It treats workflows as Python code, which makes the graph programmable and easy to version. The DAG object sets the schedule and the common defaults, and each operator becomes one task in the workflow. The arrows at the bottom define the dependency chain. One task can fan out to two tasks, and another task waits on the containerized step before it runs. Being early gave Airflow a head start, but it also meant the design could not borrow lessons from later tools. The most useful critique is not that it fails, but that some of its limits become obvious once you try to build more flexible machine learning workflows. A monolithic setup packages the workflow too tightly, so steps with different dependencies are awkward to isolate. You can work around that with Docker operators, but the setup starts to feel forced instead of natural. Without parameters, the same workflow cannot easily be reused for different experimental settings. If the learning rate changes, the workflow structure often has to be duplicated instead of reused with a new value. Static graphs are a problem when the number of tasks depends on data discovered while the job is running. If the workflow needs one prediction step per record and the record count is unknown ahead of time, the graph cannot expand to match it. Later orchestration tools try to fix those constraints by making workflows more dynamic and more suitable for modern container-based deployment. That shift changes both how the graph is written and how much freedom each task has when it runs. Prefect keeps the Python-first style, but adds the flexibility that Airflow lacked. The workflow can accept parameters and adapt its structure at runtime, which makes experimentation easier. Prefect can run tasks in containers, yet that is not the central abstraction. You still end up handling Docker details yourself, so the workflow layer does not fully absorb the infrastructure layer. Argo takes the container idea seriously by isolating every step in its own container. The YAML definition keeps the step, its image, and its requirements together, which makes the deployment model very explicit. The first template flips a coin with a tiny Python script, and the later steps branch on the result using the when conditions. Each branch runs in its own container, so the workflow combines conditional logic with containerized execution in a very direct way. The main limitation is deployment friction. If the workflow expects a Kubernetes cluster, then reproducing that environment on a laptop usually means adding another layer of tooling just to test the same graph locally. Kubeflow and Metaflow try to reduce the gap between notebook work and production runs. The point is to let a data scientist keep the same workflow logic while the platform handles the infrastructure differences. Even with those abstractions, they do not replace scheduling and orchestration entirely. Kubeflow pipelines sits on Argo and Kubernetes, while Metaflow can target AWS Batch or Kubernetes, so the lower layers are still doing the heavy lifting. Both systems support dynamic workflows, which is a major step forward. The difference is in user experience. Kubeflow often asks for extra Docker and YAML definitions before the Python workflow can be assembled, so the abstraction comes with its own overhead. Metaflow pushes that boilerplate down into Python decorators. A step can declare its libraries, memory, and compute needs, and the system builds the right container automatically. That design makes it easy to move between a laptop and the cloud without rewriting the workflow. Small steps can stay local, while heavy steps can be sent to batch, so the environment changes with the workload. The start step loads data and fans out into two model training branches. One branch stays lightweight with a specific Python environment, while the other uses batch resources and GPUs. Both feed into the ensemble step, which combines their predictions before finishing. An ML platform provides shared infrastructure for building, deploying, and operating machine learning systems. The goal is to reduce duplicated work so different ML applications can rely on the same tools. A recommender team often has to solve the hardest deployment problems first: feature management, model management, and monitoring. Once those tools are mature, other ML teams can reuse them instead of rebuilding the same machinery from scratch. That shift matters because ML is spreading across more products and workflows. When the same deployment stack serves multiple applications, teams move faster and the company avoids maintaining a separate toolchain for every model. The exact boundaries are still fluid, so different companies define an ML platform in slightly different ways. The parts that show up most often are the tools for developing models, storing models, and managing reusable features. A tool has to fit the environment around it, not just its own feature list. Two practical checks are whether it works with your infrastructure and whether you want to run it yourself or use a managed service. The first question is compatibility. If the platform only supports a narrow set of cloud providers, it can force awkward infrastructure decisions before the ML system is even running. Models do not live by themselves. They need compute behind them for training, serving, and scaling. A platform becomes much less useful if it cannot fit into the cloud or on-prem setup you already operate. The second question is who operates the tool. That choice affects how much control you keep, how much maintenance you take on, and how your data is handled. Open source usually means more control and easier self-hosting, which can help with privacy and security concerns. Managed services shift the operational burden to the vendor, but they can raise compliance questions unless they support deployment inside your own cloud environment. With those selection criteria in mind, model deployment is a good place to start. It is the point where an ML model leaves development and has to operate reliably in a real system. Model deployment is the step where a trained model becomes usable in production, so predictions can actually reach users and other systems. The main question is how to package the model, expose it safely, and serve the right kind of prediction at the right time. A deployed model usually lives behind an endpoint that production systems can call. For online prediction, that call triggers an immediate response. For batch prediction, it retrieves results that were computed ahead of time, so the delivery pattern changes even though the model is the same. A deployment service takes care of two practical jobs: shipping the model and its dependencies and making it reachable as a service. That space is fairly mature, which is why cloud platforms and specialized tools offer many options for serving models in production. The tricky part is that online serving and batch serving are not equally simple. Small-scale online prediction is usually straightforward, but batch prediction often needs separate pipelines, and batching requests for an endpoint is not the same thing as true batch inference over a dataset. Deployment is not only about serving traffic, it also has to fit the testing strategy. Techniques like shadow deployment, canary release, and A/I/B testing help expose model problems before full rollout, so the deployment tool should make those checks practical to run. A model store solves the problem of keeping a deployed model understandable after it leaves the notebook. The real issue is not just storing bytes. It is preserving enough context to identify, debug, and maintain the model later. A binary in S3 may let production load the model, but it does not answer who built it or how to trace a failure back to the right person. Once a model serves many teams, that missing context becomes a maintenance problem as much as a storage problem. A mismatch between local and production outputs usually means the model is only one piece of the system. The real question becomes which part drifted: the binary, the feature list, the featurization code, or the data pipeline around it. That list of possibilities is useful because it narrows the search space. Instead of treating the model as a black box, you start checking each artifact around it in turn. If the wrong binary was uploaded, the fix is about versioning and release discipline. The system needs a way to tell exactly which model artifact was promoted. That is the simplest failure mode, but it is not the only one, so the store has to capture more than the model file itself. A correct model can still behave badly if it receives the wrong inputs. Keeping the feature set alongside the model makes it much easier to compare training time assumptions with what production is actually using. Even when the model and features match, the code that turns raw data into features can still be stale. Featurization logic often changes quietly, and a small change there can shift predictions in a big way. That is why the model store needs to remember the code path that produced the features, not only the final prediction model. And if that code is right, the next place to inspect is the pipeline that feeds it. A broken pipeline changes the data before the model ever sees it. At that point, debugging depends on being able to connect the deployed model back to the exact processing steps and data version that shaped it. Without the generation code, you cannot reliably reconstruct how the model was built or compare it with what is running in production. That becomes even harder when the original author is unavailable, so the organization has to own that knowledge, not just the individual. That is why a model store records more than a serialized model. The goal is to gather the artifacts that make reproduction, debugging, and auditing possible, and many of them belong in a model card as well. The model definition describes the structure of the model itself. For a neural network, that means the architecture and loss, so you can rebuild the same shape later. Those structural details matter because the parameter values only make sense when paired with the right architecture. If the shape is wrong, the stored weights are not enough to recover the model. The parameters are the learned numbers inside the model. They are what training produces, and they are what let the defined architecture make predictions. A model only becomes reusable when the learned values are paired with a structure that knows how to interpret them. Some frameworks package both together, which makes restoration much simpler. Prediction is not just calling a model object. There is usually a small program that turns a request into features, feeds those features into the model, and returns the result. Those functions capture the contract between the outside world and the model. When they are wrapped in endpoints, production systems have one place to call instead of recreating that logic in every service. The code can be right, and the model can still fail if the environment is wrong. Dependencies are part of the model's identity because they determine whether the model can actually run the same way again. A container is a convenient way to freeze those runtime requirements together. That way, the same versions of Python and libraries travel with the model instead of being guessed later. Training data is part of the story too, because the model reflects the data it saw. If you cannot identify that data, reproduction and review become much harder. A pointer to the dataset is often enough as long as it is versioned. With that link, you can recover the exact training set instead of relying on memory or an old file copy. The generation code is the script or notebook that created the model. It connects all the choices together: framework, training process, data split, and hyperparameters. That code is worth storing because it explains how the model came to exist. Without it, you may know the final artifact, but not the path that produced it. The details in that code are the details that often get lost first, so it helps to spell them out explicitly. The framework tells you what tooling and serialization format the model depends on. That matters when you try to reload or port the model later. Training behavior is another piece that affects whether you can reproduce the result. Training details capture the process, not just the outcome. They help explain why two models with similar code can still behave differently. The data split also matters because it changes what the model learned and what was held out for evaluation. Recording the split rule lets you rebuild the same evaluation setup. Without that, metrics are hard to trust because the comparison may not be apples to apples. Search spaces also belong here because experiment results depend on how broadly you explored them. The number of runs tells you how much searching went into the final model. That context is useful when you want to understand whether a result was a quick trial or a long tuning effort. The hyperparameter range gives the boundaries of that search. Knowing the range shows which settings were even possible during tuning. It helps explain why the final choice was made and what alternatives were rejected. The final choice matters too, because that is what actually shipped. The final hyperparameters are part of the exact recipe for the shipped model. If you want to reproduce performance, you need the specific settings that produce that result. Notebook-driven development works fine for one person, but it breaks down when the notebook is lost or never checked in. A model store helps the company map a deployed model back to the code and context that created it, even when the original author is gone. The model itself is only the final artifact from training. The surrounding experiment outputs tell you how it performed and how it changed along the way. Graphs and raw numbers from training give you evidence about model behavior. They're what you inspect when you want to compare trials or explain why one version was chosen over another. Tags make the stores searchable. They're the lightweight metadata that helps people find the right model without already knowing its exact artifact name. Owner and task are two common tags because they answer practical questions fast. Who is responsible? And what problem does the model solve? That makes handoffs and filtering much easier. In practice, companies spread these pieces across S3, container registries, data warehouses, experiment trackers, and serverless endpoints. A README can point to all of them for a while, but a manual map is fragile and easy to lose. That fragmentation is why model stores remain an active problem, even for popular tools like MLflow. The fact that teams still struggle with artifact storage and access shows how much room there is for better tooling. The chart on the side reinforces that point. Many of the common questions are about storing and retrieving artifacts, not about training models. The pain is in the bookkeeping around the model, and that is exactly what a model store has to address. This figure is the evidence for the tooling gap. The important detail is not just that MLflow is widely used, but that users still ask basic questions about artifact management. Stitch Fix treats the model as a bundle of linked assets, not a lone file. That bundle includes the serialized model, the runtime environment, the git commit, and ownership metadata, so the model can be found and understood later. The figure lays out the same idea visually. Model, environment, code version, and tags all live together as one record. That structure makes debugging and discovery much easier than searching separate systems by hand. The point of this layout is coordination. When the artifacts sit together, anyone on the team can trace a production model back to its code, its dependencies, and the person or team responsible for it. A feature store sits at the center of how teams manage, compute, and keep features consistent across machine learning systems. The term sounds simple, but it covers a few different problems that matter in practice. Those three problems are the useful way to think about a feature store. One part is organizing and sharing features. One part is producing feature values from data, and one part is making sure training and production use the same logic. Feature management is about knowing what features exist, who can use them, and how they are shared across teams. In a large company, the same feature can be useful to many models. So, a central catalog saves duplication and helps people discover what already exists. That reuse becomes valuable when different teams solve related problems. A churn model and a conversion model may need different targets, but they can still rely on many of the same signals. So one useful feature can spread across the organization instead of being rebuilt everywhere. A feature store can act like a catalog for those shared features, and it also enforces who is allowed to see sensitive data. That matters when some features depend on private financial or user information, because sharing the wrong feature can create security and compliance problems. The second job is turning feature logic into actual values. A feature may be defined in a clean sentence, but the system still has to go read data, run the aggregation, and produce the number a model will consume. A good example is a feature like yesterday's average meal preparation time. The definition is simple. The work happens when the system calculates that average from the underlying records and turns it into a usable value. If that computation is cheap, running it on demand is fine. If it is expensive, it makes sense to calculate it once, store the result, and serve that stored value whenever a model needs it. That is why a feature store can behave a lot like a warehouse for features. It does not just describe them. It can also materialize them and keep the computed values ready for later use. The third problem is consistency between training and inference. If the same feature is built one way for historical training data and a different way in production, the model sees two different realities. That mismatch often appears when the training path uses batch data and the serving path uses streaming data. Add another layer of complexity, and development may be in Python, while production uses Java or C for speed. So the same feature logic gets re-implemented for two environments, and that creates room for drift. It is tedious, and even a small difference in code or timing can make the model behave strangely in production. Modern feature stores try to remove that split by keeping one definition for both training and inference. When the feature logic is shared, the model is much less likely to train on one version of the world and serve on another. The category is still young, so vendors do not all provide the same capabilities. Some manage definitions only, some also compute features, and some add validation to catch schema mismatches before they become production problems. Feast is the best-known open-source option, while Tekton and cloud platforms each offer their own version of the idea. Adoption is still uneven, and many companies either skip a feature store entirely or build one internally because their needs are so specific. Build versus buy decisions shape how much control, speed, and staffing your ML stack will need. The real question is not which option is better in general, but which option fits your company's needs and constraints. The right infrastructure depends on what applications you run and how large they get. A small set of use cases can live with simpler systems, while a broader or higher volume workload pushes you toward more specialized infrastructure. Ownership changes the staffing picture immediately. Managed services reduce the amount of operational work, while self-hosted systems usually demand more engineers to run, tune, and maintain them. At one extreme, a vendor handles almost everything end-to-end. Your own team mainly moves data in and predictions back out, which keeps the internal platform very small. At the other extreme, sensitive data or strict control requirements can force a company to own the full stack. In that case, even the physical infrastructure may stay inside the company's walls. Most teams split the difference. Some pieces come from cloud or SaaS providers, and other pieces are built internally where the business needs more control or customization. Three forces come up again and again: company stage, strategic focus, and tool maturity. Those factors often matter more than a simple build or buy rule of thumb. A company's stage changes its trade-off. Early on, speed matters most, but as usage grows, the economics of buying versus building can flip. Early teams often choose vendor tools because they need to launch quickly and conserve limited engineering time. Later, once usage and spending rise, a custom system can become the cheaper path. The next question is strategic focus. If the infrastructure is close to your competitive edge, you may want to own it. If it is not central to the business, buying usually makes more sense. That rule matches what many infrastructure leaders say in practice. Non-technology companies often prefer managed services and point solutions, while tech companies usually want more control, more modularity, and more room to customize the stack. Tool maturity can force the decision for you. Even if buying would be preferable, you may still have to build when no vendor product is ready for the problem you need to solve. When a market is immature, teams often assemble their own solution on top of open source components. That gives them the capability they need before the commercial ecosystem catches up. That pattern shows up across the industry. Early adopters build custom systems because the tools do not exist yet, and later vendors struggle because those custom environments are all different and hard to integrate with. That is why selling in a big tech can be so difficult. The product may be good, but the effort to fit it into a heavily customized stack can consume the team before the core product even gets a chance to shine. Building adds more engineers, but it also adds long-term opportunity cost. A custom stack can make it much harder to adopt new tools later, because every new system has to fit the old integrations. These decisions depend on the company, the market, and the stack already in place. The important habit is to weigh the trade-offs explicitly, because vendor selection becomes a major part of the infrastructure job as the space keeps changing. Infrastructure is the layer that makes ML usable in practice. The main ideas here are the systems, tools, and trade-offs that let models move from experiments into production. A model does not reach production by itself. People need storage, compute, deployment paths, and the right environment around it. That is why ML adoption is as much an infrastructure problem as it is a modeling problem. Storage and compute are the first layer because every ML project depends on data and heavy processing. Cloud services make that layer easy to start with. But at larger scale, the bill can become a serious concern, which is why some companies revisit whether cloud is still the best place to run everything. The development environment matters because engineers spend most of their time there, so small improvements have a direct effect on productivity. When a team uses the same setup, people spend less time fighting differences in tools and more time on the work itself. Resource management grows from simple scheduled tasks in a full workflow coordination once ML jobs have dependencies, retries, and shared resources. ML pipelines need tools built for that shape of work, which is why systems like Airflow, Argo, and Metaflow matter. As ML teams mature, platform work usually concentrates around a few recurring needs. Deployment gets models into use. The model store manages versions and reuse, and the feature store keeps training data and serving data aligned. Infrastructure always leads to a practical decision about where the team should invest its effort. The right choice depends on scale, urgency, and how much control the organization needs over the system. A reference like this points to one of the broader arguments behind the chapter. Infrastructure choices shape how a technical system grows, just as business systems do. Tesla's AI Day is a useful example of how large-scale compute becomes a real engineering discipline. It gives a concrete picture of the hardware and system planning behind serious ML workloads. Reasonable scale is a reminder that infrastructure should match the size of the problem, not some abstract ideal. A lot of ML systems work well without heroic complexity if the team keeps the design aligned with actual workload needs. That acronym points to the large companies whose infrastructure choices often influence the rest of the industry. Their scale makes the trade-offs especially visible. Examples like Uber and Zillow show what happens when data systems have to handle very large volume with tight latency requirements. They make the storage and pipeline discussion concrete rather than theoretical. Open data problems often come from scale, ownership, and the difficulty of keeping many systems consistent. That is part of the same infrastructure challenge running through the chapter. Even the dictionary definition matters here, because infrastructure is the supporting structure that makes other work possible. That definition fits ML especially well. A split like that creates friction because engineers have to work across systems that do not behave the same way. Extra platforms usually mean extra operational overhead and less smooth collaboration. The focus here stays on storage because the broader data system picture already appeared earlier in the book. Narrowing the scope keeps the infrastructure discussion centered on what ML teams need most at this point. Memory requirements give a rough sense of how modest many ML jobs are compared with the giant machines people sometimes imagine. In practice, a well-chosen machine often matters more than an oversized one. Operation Fusion is one of the ways model execution gets faster by reducing overhead between steps. That kind of optimization becomes important when compute cost and latency matter. Flop/S is a common way to talk about raw compute throughput, but it is not the whole story for real performance. Bandwidth, memory access, and the shape of the workload also matter. Flops and bandwidth are the two numbers that often decide whether a deep learning system is efficient or slow. Thinking about them together gives a better picture of where the bottleneck really is. Virtual CPUs are cloud abstraction, so the number on the invoice does not always match the number of physical cores in a simple one-to-one way. That matters when you size machines for ML jobs, because CPU layout affects how much parallel work you can actually get done. That cost shows why raw compute can become expensive very quickly at scale. A single machine may look reasonable in isolation, but repeated use changes the economics fast. On-demand capacity gives reliability, while spot capacity trades reliability for lower cost. Choosing between them is really about how much interruption a workload can tolerate. That industry trend reinforces the same point. Cloud spending has become a major part of enterprise infrastructure. The economic balance between cloud and private data centers is no longer a niche question. Cloud convenience comes with a real long-term cost, and that tension drives many infrastructure debates. The hard part is separating short-term flexibility from long-term expense. That work is often cited because it captures why cloud economics can surprise teams as they grow. The build changes the architecture discussion very quickly. Multicloud usually enters the picture when organizations want flexibility, resilience, or leverage across vendors. It also adds complexity, so the benefits have to justify the extra coordination. That argument helps explain why infrastructure decisions rarely have a perfect answer. Different organizations value control, portability, and cost in different ways. This is a useful companion reference for the practical side of data science infrastructure. It reinforces the idea that strong systems design is part of good ML work. Free GPUs lower the barrier to experimentation, which is why tools like Collab are so attractive for learning and prototyping. They're a good reminder that infrastructure choices also shape access. Notebook workflows become much more useful when they are treated as part of an engineering system rather than as isolated scratch space. Netflix's work is a good example of that shift. A pull request is the unit of change that moves code through review and into the shared project. That idea matters here because infrastructure work often needs the same kind of control change process. The editor debate is a familiar example of how technical preferences can become deeply personal and long-running. It is a light reminder that tooling choices often provoke strong opinions. Kubernetes is a useful example of the gap between infrastructure complexity and the daily needs of data scientists. The recurring complaint is that platform tools should hide orchestration details unless those details are truly part of the job. Borg is an important historical example because it shows how large-scale cluster management evolved into a serious systems discipline. Ideas from that work still echo in modern orchestration systems. Online prediction is simple because the request and response happen immediately through an endpoint. Batch prediction is different because it is scheduled work, so the system has to manage jobs and store results for later use. Feature stores exist because training and serving need the same features in a consistent form. When teams separate feature logic from model code, they reduce duplication and make production behavior easier to control. Michelangelo is a useful example of an internal ML platform built around the practical needs of a large organization. It shows how platform tooling grows when ML becomes a shared capability. Feature transformation is another name for the same idea of turning raw data into model-ready inputs. Different teams may use different terms, but the underlying pipeline step is the same. Comments like this often capture the practical instincts behind ML infrastructure design. The repeated theme is to keep the system useful for the people who actually build models.